let's suppose that we have a set, which I'll depict by a blob like this, that has 3 elements. So when I say it has 3 elements, that means they're distinct, so there are these distinct dots that represent the elements, and they're non-equal things. Now, this idea of, quote, having 3 elements, this is a property that a set can have, which we have yet to define, and actually our goal today is to define something like that. Let me skip ahead a bit in the notes just to show you what I mean. Here in definition 120, part 1, you can see where we define in a rigorous way what it means for a set to have n elements. It means this, which is something we're about to define. But for now, definitions aside, let's just pretend we know what it means for a set to have 3 elements. We think it means that it consists of some x and some y and some z, such that x and y are different, and y and z are different, and x and z are different. Something like that. So I can depict it like this. And let's say you have another set which has 4 elements, or just more than 3, maybe 5. Then what I want to do is think about the possibility of having injections or surjections or bijections from one to the other. So can we have an injection, a surjection, a bijection? Well, let's think about injection first. Is it possible to inject a set with 3 elements into a set with 5 elements? So an injection means a function. So for each dot here, I get to draw an arrow and send it to one dot over there, right? And specifically for an injection, I can never send 2 dots to the same place, right? So like if I did this, then that would not be an injection. But I can do this, and that is an injection. So it seems, yes, an injection is possible. What about a surjection? So to have a surjection from this set to this set, I would need to send each, I would have to be a function, so I'd have to send things over somehow. And it's allowed to not be an injection, so I can do this if I want to. But for it to be a surjection, there has to be nobody here left behind. But look, with the way it's done so far, these guys get left behind, right? And it seems like no matter what I choose, no matter how I send these points over, no matter what I do, some guys are going to get left behind over here, and you will have something that's not a surjection. So it seems like a surjection is not possible in this configuration, and it seems like the reason it's not possible is that there are just not enough points back here to get everything over here, right? Like there's only 3 here, so at most you're only going to get 3 points over here that get touched by a green arrow. Now, you could try to do this and send multiple arrows out from just one point, right? But then you're looking at not a function. When we say surjection, we mean a surjective function. Injection, we mean an injective function. So it seems that in this configuration, a surjection is not possible. And so a bijection is also not possible. Okay, so here I'm not trying to prove anything because I haven't defined anything. There's not even any actual math notation on here. But I'm just trying to give you the sense that a surjection from a set to a set that has more elements doesn't seem to be possible. And what's preventing it is that there are too few elements back here to get all the elements over here. So this idea of being able to express that there are too few elements back here to get everyone over here, this idea is going to help us get at the idea of counting how many elements are in a set. So here we can we can't count yet, but we can at least compare and say, look, the impossibility of a surjection from here to there suggests that maybe this set has too few elements for a surjection to be possible. Well, let's try a different configuration and then ask the same questions. So this time, let me put 5 dots over here, and then only 3 dots over here. And then I'll ask, is an injection possible? Is a surjection possible? Is a bijection possible? And now a surjection seems possible, right? I can just easily make sure everybody has a friend. So these guys all have friends now. And I have to send this somewhere. It doesn't matter where I send it. And there we go. Surjection is totally possible. So this is what a surjection kind of looks like. The way I like to think about it is that the points back here in the domain sort of get clustered up like this, where each cluster of points is getting sent to the same place. So to come up with a surjection is kind of like coming up with a way to cluster up these points back in the domain and then make the clusters match up with certain points over here. Anyway, definitely a surjection is possible. What about an injection? An injection from this set to this set, is that possible? So let's get started. So okay, if I do this, that's not an injection, right? I have to send things to different places. So 2 points can never go to the same place. All right. Could I stop here? No, that would not have the correct domain, right? The question here is, can we have an injection from this set to this set? So meaning, if I call this set X and that one Y, can I have an injection mapping X to Y? The domain has to be X. The range doesn't have to be Y, it just has to be a subset of Y, but the domain has to equal X. So this is not good enough right now. I need to send this somewhere. But do you see the trouble? There's nowhere I can send it where I haven't already sent something. No matter where I send it, there's going to be some conflict that makes this not injective. So then an injection is actually impossible, which means also a bijection is impossible, since a bijection has to be at least injective. And I hope you're now also getting a sense for why it's impossible. It's that there are too many elements here and too few here to go with them for us to make an injection. There are too few here. When you try to build a function, each one of these is, if you try to build an injection, then each one of these is going to get matched up with just one thing from back here, right? And there are too few of them to get matched up with everybody. Or you can think there are too many of these. 2 of them must end up going to the same place. And finally, if I draw, I don't know, let's say 4 dots here and then 4 dots there, where it's the same number of dots, then in fact a bijection should be possible. And you can easily just send points over in any way, but if I want to make it look fancy or something, I can do a little swap there, whatever, it doesn't matter. What the picture looks like, this is definitely a bijection, so a bijection is possible. Now I'm not saying every map from this set to that set is a bijection, I'm just saying there exists a bijection. So I could totally do this, for example. Then this would fail to be injective because of this 2 arrows coming to the same place, and it would fail to be surjective because of this being left with no friend over there. So also a non-bijection is possible, but also a bijection is possible. But do you see that the possibility of a bijection, even the existence of a bijection between 2 sets, really tells us a lot about how they compare in terms of numbers of elements. The existence of a bijection, well, first of all, it means there was an injection, right? And that can only happen if there's not more elements on the left side than on the right. And the existence of a bijection also means a surjection was possible. And a surjection can only be possible when there's not more elements on the right than there are on the left. So when a bijection is possible, it seems like you've got the same number of elements on the left and on the right. This suggests the following interesting relation that two sets can have to each other. So let's say you've got two sets A and B. Then here's an interesting relation. The existence of an F, such that F maps A to B, and F is bijective. The possibility of there being a bijection, the existence, that seems to be an important relationship between two sets A and B. It tells you something about somehow the number of elements, whatever that means. So we're going to make this a definition. We'll say A wiggly equals B if and only if this is true. So this wiggly equal sign, we'll have a way of reading it in English, which is, so this is sort of the formalism, I'm going to use that notation. And then the semantics, the way we read this in English is A has the same cardinality as B. And notice I'm not really defining the word cardinality. I'm just defining the phrase has the same cardinality as. So I'm only defining that phrase, and I'm not defining the word cardinality by itself. So this is a definition, an official definition. Definition 114, part 1 here. So A has the same cardinality as B if and only if there's a bijection from A onto B. Notice that the F is bound here, so this is not saying anything about F in particular. It's only a relationship between A and B. Now what about these other ones? Hopefully you saw that this is pretty interesting also. The existence of an injection is pretty interesting. For there to exist an injection from A to B, so we're going to use this symbol. And usually I'll just read this as there is an injection from A to B. But for there to exist an injection from A to B seems like it requires that there not be any more elements in B than in A, or that there be no more elements in... Sorry, I think I misspoke there. The existence of an injection requires, if this is A and that's B, the existence of an injection requires that there be no more elements in A than in B. So the notation here like sort of suggests the right thing. It looks a little bit like a less than or equal to symbol, and it's saying A has fewer elements than B. So you can read it that way if you want. A has fewer elements than B. But one very interesting thing about this definition is that there's no mention of numbers. There's no mention of natural numbers, right? We're somehow talking about the numbers of elements that sets have, whether one set has more elements than another, whether two sets have the same number of elements, but there's no mention of number, right? So this definition could have totally been introduced well before all of this stuff that I'm scrolling through here, well before the natural numbers were introduced. So somehow it seems that there's a way to talk about the number of elements in a set, or at least there's a way to to compare the numbers of elements in two sets without having a concept of number at all. So just knowing what function is and what it means for a function to be bijective, you can say two sets have the same number of elements, whatever number means, as long as there exists a bijective function from one to the other. I think this is really very interesting that this is a part of our formal development, because this is probably, I mean, I don't know if this is historically true, but I'd like to imagine at least that this is how people would compare numbers or the sizes of sets before they had the ability to count up to a certain number. So, for example, you can imagine that there are maybe two shepherds and they want to split some bunch of sheep evenly among them or something for some trade or something like that. And there are a bunch of sheep here, more than these guys have numbers in their language to refer to. So these guys can't express like, oh, I have this number of sheep. They just don't have a word for this number. They don't have language to count up that high. Well, one thing they can do is try to establish a bijection between this collection and this collection, which they may not have had the same rigorous formalism that we have, but they still have the ability to set up a one-to-one correspondence, which is what a bijective function is. So maybe they could pair up sheep, just making sure not to repeat, by which I mean making sure not to like pair two sheep from here with one sheep over there. That would be not a non-injection. Or pairing two sheep from here with two sheep with one sheep from there. That would be not even looking at a function. And then they could see at the end. So if there's nobody left over at the end and everything's matched up perfectly, then they would say, okay, we have the same number of sheep. Although they probably wouldn't, they might not say that because they don't have a concept of number. But they have the same like total amount of sheep. So even without counting, they can compare numbers, right, by establishing a bijection. But if after pairing them up, there was one left over here, then you have something that's not a surjection, then they would know, like, okay, he has more sheep here because there's one left over. But what about us? We definitely have a concept of number. We just finished defining the natural numbers. So why are we taking this weird abstract route for defining what it means for two sets to have the same number of elements? Why don't we go ahead and use numbers? Well, we have finite numbers, right? But actually, there's a huge advantage for us in the fact that these definitions don't rely on numbers. You can apply these definitions to any pair of sets. So even possibly not finite sets, you can talk about whether they have the same number of elements. And when you talk about number of elements in this sense, that's called cardinality. So again, I haven't defined the word cardinality. I'm not defining it, although it's possible to define it, but I'm not defining it. I'm just defining the phrase has the same cardinality as. So I'm sort of leaving, and this happens often in math, that you can define what it means for two things to have a certain attribute being the same between them before you're able to easily define what that attribute is in the first place. Okay, well, if I'm really defining an attribute here, if this idea of A wiggly equals B is really some kind of, is talking about A and B sharing some attribute, then there are certain things that ought to be true. First of all, A should have that attribute for A should be the same between A and itself. It's so built into the language of things having attributes that it's hard to even express it in a way that doesn't sound trivial. But if you think about this statement, it's not immediate. It requires us to prove that there exists a bijection from A to itself. So this property, so this is a theorem, so this needs proof. This property is called reflexivity. And this we can prove right away. So to prove there exists a bijection from A to itself, we need to do an existential generalization, right? We need to find one, find an example. And here is an excellent candidate for at least a function from A to itself, the identity function. And Unfortunately, we don't state in here that it is a bijection, but you can prove pretty easily that it's a bijection. So that's how you would establish that sets have the same cardinality as themselves. Let's also think about this one. So to say, if this statement is talking about A and B sharing a certain attribute, then if A has that attribute being the same as B's version of that attribute, then B should have it the same as A. So if A has the same cardinality as B, then B should have the same cardinality as A. That's if it makes sense to think of this predicate regarding A and B, if it makes sense to think of this as A and B having the same something. If it makes sense to think of it that way, then these three things ought to be true. So the first one we were looking at is reflexivity. Now let's look at symmetry. So let's write the proof for this one a little bit more carefully, just to practice a bit with the definition. So now assume A has the same cardinality as B. Then what I'm assuming is something that has an existential quantifier in it, right? So I wouldn't usually spell it out, but since this is our first time using it, let me spell it out. What we know is that there exists something which maps A to B and is a bijection. Usually I write on to B, but we don't have to write that part. Okay, then my goal is to prove that there exists a function from B to A that is a bijection onto A. So that's my goal, right? So how do I make use of this? Existential instantiation, right? So we can get then let me be lazy and copy this. And it doesn't make sense to say and anymore. I should say such that. So we can get a bijection. Then now it looks like I've unraveled or unwrapped or made the most use that I can of my assumption that A has the same cardinality as B. So how can I prove from this situation that B has the same cardinality as A? I must prove that there is a bijection B to A. So I don't have to use F to build my bijection from B to A. If I can just make one up out of nowhere, then I would do that. But I don't have very much information about A and B except that F is a bijection from A to B. So somehow I should probably use F. Okay, well if I have a bijection A to B, how would I build a bijection B to A? Remember Theorem 75 back here? I know it's been a while, but basically it says what we want here exactly. If you have a bijection x to y, then the reverse is a function. The reverse being a function happens anytime your function is injective, so bijection is injective, so at least the reverse is a function, but also it maps y to x. So sometimes when you don't have surjectivity, if you just have an injection, then when you take the reverse, you don't quite get y. You don't quite get the original codomain sitting in here as the domain. But for bijection, it does. So Theorem 75 basically says what we want. By Theorem 75, F inverse maps B to A, and F inverse is bijective onto A. So thus, and now this is the existential generalization, thus we have found a function mapping B to A, which is bijective onto A. So we have proven this. So this is done, but keep in mind as you think about these, that these pictures with finite collections, these pictures with these finite collections, these are just to get us started thinking. The situation here is extremely general. These are just any old sets. So we have no reason to think that we can express these sets as just a bubble filled with dots. So the concept here has already gone much, much further than the pictures that birthed it. Okay, so there's a There's also transitivity that one would like to check. If A and B share a certain attribute and B and C share that attribute too, then A and C ought to, right? So these are all justifying that you can think of cardinality as a kind of attribute that a set has, even though we have not defined any actual attribute called cardinality. All we've done is defined what we think it means for two things to have the same of that, the same cardinality. So you find anytime there's a relationship between two things, like this wiggly equals here, you find in math that these properties are referred to a lot, and they're very important. Reflexivity, symmetry, and transitivity. When you have these together, that's when you can actually think of your relation as describing some attribute that things are sharing. So when you have all these, reflexivity, symmetry, transitivity, you say that your relation is an equivalence relation. And if you take more math classes, you will almost certainly encounter this concept many times and in more depth than we're doing here. Now, for our sort of curvy less than or equal to symbol here, which only describes the existence of which only expresses the existence of an injection and not necessarily a bijection, you don't get the equivalence relation properties. You only get two of them, reflexivity and symmetry and transitivity, but you don't get symmetry. Actually, if you look back to our work with natural numbers, going away from this cardinality discussion for a sec, we had, for natural numbers, we had this less than symbol and we have the less than or equal to symbol. And shortly after we proved this theorem, trichotomy for the order, this exercise comes up, which some of you have done for your presentation, as part of your presentation. And it's this property that if n is less than or equal to m, and m is less than or equal to n, and they're natural numbers, then n equals m. So this is what you get instead of symmetry. So for ordinary, not the curvy, weird less than or equal to that we just introduced, but for ordinary less than or equal to for natural numbers, you don't have symmetry. Symmetry would mean if n is less than or equal to m, then m is less than or equal to n. You don't have that. But what you have is this. This is called antisymmetry. And that turns out to be what you also have for the weird curvy less than or equal to symbol. If there exists an injection from A to B, and there exists an injection from B to A, then there exists a bijection from A to B. So you can see this theorem has three names on it, Cantor, Schroeder, Bernstein. So this is, and even has a preliminary lemma that helps to prove it. So whenever you see names on a theorem like this, that means it's serious business, and the proof will be pretty involved. All right, so I'm not going to get too much into that because I want to get a chance to spend time working with finite sets, which we'll go to very soon. But I would like to oh, I remembered. I need to just tell you how to write these things in LaTeX. So if you want to write this symbol, having the same cardinality as symbol, you can do this in math mode, approx. And for this symbol, you can do so if you just do prec like this, then it'll be this curvy equal symbol, curvy less than symbol like that. But if you do prec equals, then it'll be that symbol. And definitely don't mix them up. Like usually in my handwriting, I exaggerate the curvature of it so that I don't mix them up. Don't mix up this and this. Maybe here's one way to drive that warning home. There's a theorem that will take a bit of effort, which relates them. And if in your handwriting you don't distinguish them, then it'll be very difficult to actually relate them. So this is for natural numbers. And Actually, you can understand what these theorems are saying right now, even though we haven't gotten to it. Like this is saying two natural numbers have the same number of elements if and only if they're the same natural number. Now, we haven't thought very much about the elements of a set of natural numbers. Sorry. We haven't thought very much about the elements of a natural number. But we have kind of. Because our less than relation for natural numbers is really just membership. Anyway, we'll get to it.